Welcome! Today, we're going to take a trip to a world where 10 doesn't actually mean 10. It sounds weird, I know, but by stepping outside our own number system, we're going to uncover some really cool hidden rules that we follow every single day without even realizing it.
Okay, let's just dive right in with a question. It seems super simple, but the answer, well, it's surprisingly deep. When you see these symbols, a 1 and a 0, side by side, what number pops into your head? 10, right? Of course it is. But what if I told you that's not always true?
Here's the big secret. The symbol 10 isn't a number, it's a code. And what it always means is one full group of whatever your base is and 0 extras. So, in our normal world, our base is 10. But what happens if we decide to change the size of that group?
To figure that out, let's jump into a totally different system. And this one is actually super intuitive because it's connected to something we all have. We're going to explore a system built entirely around the number 5.
I mean, think about it. Way before we had calculators or anything, we had this perfect counting tool right at the end of our arms. The 5 fingers on a hand give us a really natural reason to group things in fives. And a lot of ancient cultures actually built their entire number systems around this exact idea. So this idea of a grouping size has an official name. It's called a base. Our everyday system is base 10 because we group everything by tens. The system we're exploring today is called Base-5, or sometimes the quinary system. Here, everything, and I mean everything, revolves around grouping by 5.
All right, let's actually see how this works. We're going to learn how to count in this brand new world. Now, it's going to feel a little strange at first, for sure, but stick with me, because what it shows us about our own numbers is pretty amazing.
Okay, here it is. The single most important rule in Base-5. You can only use the digits 0, 1, 2, 3, and 4. That's it. A single digit that means the quantity 5, it just doesn't exist. It's totally off limits in this world.
So let's try counting, right? We start at 0, then 1, 2, 3, 4. So far, so good. Everything feels totally normal. But now we have a problem. We need to count the next number, the amount we call 5, but we just ran out of digits.
So what do? I mean, how on earth do you write that next number when the most obvious symbol for it is completely illegal?
Well, you do the exact same thing we do in our base 10 system when we hit 9 and run out of digits. You regroup. You bundle those 5 single units together, and you trade them in for one full group of 5. So what do you have now? You've got one 5 group and 0 ones left over, and we write that as, you guessed it, 1, 0, which we say as 1, 0 base 5. And this just brilliantly shows that place value is this universal concept. In our familiar base 10, every spot to the left is 10 times bigger than the one before it. The ones, the tens, the hundreds. But in base 5, each spot is 5 times bigger. So you have the ones place, then the fives place, then the 25s place, and so on. It's all just powers of 5. So what's the big deal? This isn't just some neat party trick. The real magic happens when we realize what this strange new system can teach us about the one we use every single day without even thinking about it. Okay, let's take a number, the quantity 18. In our system, base 10, that's easy. It's one group of 10 with 8 ones left over. But in base 5? Well, how many full groups of 5 can you make out of 18? You can make 3 of them, right? That gets you to 15, and you'll have 3 little ones left over. So we write it as 3-3, or 3-3 base 5. It's the exact same amount of stuff, we're just describing it with a different grouping system. All right, so what does this mean for something like addition? Do you have to throw out your entire multiplication table and start from scratch? Does 2 plus 2 not equal 4 anymore? No way. The actual math underneath it all doesn't change one bit. Look at this addition table. Let's find 2 plus 3. What does it say? 10. That's because the quantity of 2 plus 3 is still 5. We just have to ask, how do we write the quantity 5 in this system? Well, it's one group of 5 and 0 ones. So we write it as 10 base 5. The amount is the same, it's just the name, the symbol we give it that's different. And this, right here, is why messing around with base 5 is such a powerful idea, especially for teachers who are trying to explain our own number system to students. It makes us slam on the brakes. You know, for us adults, adding in base 10 is just autopilot. We carry the 1 and we don't even think about why. It's just a rule we memorized.
But when you're forced to work in an unfamiliar system like this, you can't rely on memory. You have to slow down and consciously think, okay, why am I regrouping here? And in that moment, the invisible structure of our own number suddenly becomes visible. It's like you get to see it again for the very first time, through the eyes of a kid.
So, here's the real takeaway. The point of all this isn't to replace Base 10. Of course not. The real power of learning something like Base-5 is that it shines a bright light on the beautiful, logical structure of the system we use every single day, showing us something we stopped seeing a long time ago.
And that kind of leaves us with one final, bigger question. We've seen that by stepping outside our normal way of counting, we can finally understand its hidden rules. So what other invisible systems, in our language, in our culture, do we follow every day without a second thought? And what could we learn about them if we just tried to see them from the outside? Thanks for watching.